This one begins a little differently. I love silly coincidences. Today is the 26th of February. It is the 26th episode of this project. I can't believe I've done this 26 times already. It's kind of insane. And it is also exactly 6 months away from my birthday on August 26th. And sometimes silly coincidences are just enough to get me to do something I've been putting off doing, including addressing you and going through the awkward exercise of talking to this camera, knowing that you're not actually here and that it's going to take a while before it all gets processed and digested by the big machine. And somehow, for some reason, there's a set of silly coincidences that leads you to listen to this. So hi, I want to know more about you. Who are you? Where are you at? What stage of life are you in? What are you interested in? I share a little bit of what I'm into, but I would love to know from another human listening to this. And I leave my email in every single description, but there's always the comments and any kind of interaction, a liking, liking or sharing or anything like that. Make me know there's someone out there resonating with whatever conversations I'm having. And I've been loving these conversations. I hope you have too. But I'm also very well aware that people have different preferences. And I'd love to hear what those are. And I'd love to hear your reactions. And it's pretty weird. This is my first time talking to the camera like this. And it's pretty dang awkward. But I'm doing it anyway. That said, without further ado, traces Appendix 26. Jesse Rodríguez, thank you for being here today. It's great to have a chance to talk to you about research in general, physics, plasma, optics, and whatnot, and see where the conversation takes us. I am in the lucky few, or I guess not that few, who got exposed to your PhD thesis via YouTube recommendations. And I clicked on the sort of the impossible to ignore title, Optical Computing with Plasma. And I was blown away from the beginning. And there's a lot to unpack there, but I wanted to start by asking you, one of the most salient parts of the thesis defense was the little moment that you take to talk to you about your family and about the story behind your family and about how you were able to dedicate so much of your time into doing this thing that you love. And so I wanted us to go back to before we get into optical computing and before we get to plasma and electromagnetic stuff. What was your upbringing like, and what were the set of circumstances that led to this path of physics and math and nuclear stuff?
Well, it's kind of interesting because like I mentioned in that acknowledgement section of my thesis defense, uh, there's not a lot of history of academia in my family, in fact, at all. So, both of my parents didn't go to university. My dad was born in Mexico, and my mom was born in the state of Oregon, and they both kind of just come from uh, families that worked hard with their hands for essentially as far back as we know. I mean, I've I've gone back and seen the room that my dad was born in, and it still has a dirt floor, and so
Jeez.
uh, so to my parents' credit, growing up, going to university was always an expectation. It was something that I thought I knew in my mind that was sort of the plan. But I didn't really have any sort of idea beyond that. My dad got involved in the construction industry shortly after my older sister was born. So when my older sister was born, when my dad was 20, and well, my mom was 20 as well, but she had just turned 20. So they were babies, they had just gotten married. And essentially, when she came around, my dad was working in retail, and he was like, "This is not going to cut it if I'm going to support a family." And so he made a career transition into construction, and he did really well in construction, and worked his way up in the companies that he worked for, and then eventually started his own company. in Oregon called R&R General Contractors. And so my thought was, I'll join the family business, and that's an area of industry where I need to have an engineering degree to participate, and so I was going to get a civil engineering degree, and that was basically my plan. Well, when I was in high school, and it all sort of started with this. I was lucky enough to go to this summer program that was held at UC Berkeley. It was kind of like they came and did a presentation at our high school and said, "Hey, we have this summer engineering for high school students program. You can come for." It was like a kind of like a conference length. It was like 4 days, and you can kind of just meet some other young students who are interested in engineering and learn about some of the cutting edge of engineering research. And one of the topics, or one of the things that we were charged with as part of this conference, was we had to give a presentation on a future technology. And that one of the nights I was just looking on my computer for, what are the options, okay, for all these future technologies. And there was one option on the list that just stuck out to me, and I can't even really explain why. It just kind of was like
He
humming, and it
called you.
was it was
He
nuclear fusion. And I was like, what is that? And I had never heard of it. And so I read about it, and it just lit a fire in me. For some reason, I was like a moth to a flame. It was so interesting to me. And I remember that night
he
I stayed up basically all night reading about it. I was just totally infatuated with this topic. And so the next day we had a meeting to like discuss what was the topic we were going to give a presentation on. And I was just so adamant it had to be this topic. and 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 I convinced my peers that we would give that presentation. So I got to learn about that technology throughout the rest of that uh, that that conference experience.
he
And it just kind of planted a seed in my brain. This is just such an exciting uh, technological breakthrough if we're able to accomplish that. And I would love to work on this problem. So it was very. I had no clue how, when, why, in what way I would ever be able to be involved with the people who are working on this problem. In my mind, I'm still going to just be a not just because I think that being involved in construction and in building roads and sidewalks is perfectly a perfectly great way to live your life, and a really productive way to spend your time. But that was, I still wasn't thinking I was actually going to go and do research or anything like that. And then I had this great teacher in high school who was a physics teacher. His name was Michael Lampert, and he was special. He had his master's in physics. In fact, he almost finished his PhD in physics at Berkeley, and he kind of quit early because he lost faith in what he was working on, and he felt like nobody would care about it, and he kind of just decided it wasn't for him, and he stopped, and then he ended up becoming a high school teacher. Well, all
he
to my benefit, because he was spectacular. He went and acquired funding so that we could do uh, uh, big research projects in high school. And like
he
he sent students to the Intel Science and Engineering Fair, like at the national level, basically
wow.
every year. And this is just at a public school in Salem, Oregon.
Wow.
And no, this isn't a magnet school or anything like that. We just had this fantastic teacher, and I had this seed planted from the nuclear fusion thing, and so I really started. The next year, I got to take my first physics course, and it was just like I was so excited for it. I was like, okay, now I can kind of scratch the surface and learn a bit about this, and see what it's all about. And I just had a kind of a natural aptitude for it. And he pulled me aside and was like, "Hey,
he
what are you going to do with this? What's your plan?"
he
And I was like, "Well, I think I'm going to go get an engineering degree and go join the family business." And he was kind of just like, "Ah," and I was like, well, what's
he
wrong? What's going on?" He's like, I have to be honest. I think that would be a waste. He's like, I think you should, uh, you know, study physics. And I was like, well, what is, how am I going to make money doing that? What jobs does that lead to?
What does that
And he
even
was,
mean? Yeah.
yeah, what does it even mean? And he was like, well, he's like, I can't answer all of your questions, but he's like, I'll leave you with this. He's like, just ask yourself the question: if you had all the money in the world, if you never had to worry about money, what would you do then? And it just kind of stumped me. I had nothing really to say to that, and I thought about it, and I just kind of had that in the back of my head going forward, and later on, that kind of helped me. I heard his words again, and it helped me decide to go down that path ultimately. Well, anyways, time goes on. When I graduate high school, I go to UC San Diego at first as a structural engineering major. I'm still thinking going to go into the family business, but even still, at the same time, I have this kind of thing. I know what I'm passionate about. I know what I'm interested in, what I'm really interested in the back of my mind. And I think, okay, maybe I'll just add a physics minor at UC San Diego. And so I go there. I go to my academic advisor, and I say, can I add a physics minor? How does that work? And the advisor was kind of a little standoffish at UC San Diego. They were kind of like, you know what? Let's worry about that later. You're an engineering major. It can be difficult to finish on time because these are impacted majors. They're, you're taking up a spot here at this great UC school. Let's not worry about that right now. Just try to get on track. And I was like, it just really left quite a bad taste in my mouth. And then I put a lot of thought into it. I went and visited home for like Halloween in October of that first quarter. And then when I had to get on the plane to go back to San Diego, I was like, man, I'm feeling really homesick. My girlfriend at the time, who became my girlfriend in high school, who's now my wife, she was still in Oregon. And I was just like, what am I doing? And Oregon State actually has a spectacular nuclear engineering program. They even have a fission reactor on campus. And so I thought, you know what? I know what I'm interested in. I'm not 100% sure that this is going to lead to a job where I'm going to be. In fact, I'm pretty certain that I'm not going to be as financially well off of as if I go into the family business. But I know that this is what I'm passionate about. I know that there's this nuclear fusion problem that is such a strong draw to me, is what I want to learn more about. And so after just one quarter at UC San Diego, I transferred to Oregon State as a nuclear engineering major. And then so now I'm thinking, okay, I can learn a little bit about nuclear fusion. Having a nuclear engineering degree is still a strong credential. I'll always be able to support myself. It's fine. Well, at Oregon State, I start to get into this wild idea that after I took, so at Oregon State, we have these general physics courses, and it's like any other university where if you're in an engineering major, the general physics courses are like the weeder courses that try to make, they're so difficult, they try to make all the engineers quit, right? And there was this instructor named Chris Coffin at Oregon State, and he wasn't even a tenure professor. He's just an instructor, and he just wrote the most comically difficult exams. They were beautiful. They were amazing. And I took one of his exams, and I was just like, oh my God, that was so hard. It was like the hardest exam I had ever taken. And I was like, I need to understand this. And so, then I got the whole idea of doing like a physics minor or whatever just entered my mind again. I was like, man, I just really want to understand this. And I was like, you know what? I spent another late night coming up with an entire 4-year plan. And I was like, I can actually do a dual major. I can do it. I can get it done in time. And so I went to the academic advisor at Oregon State, and I had this whole plan, and I thought I was going to have to really make my case to add this major. And I showed up, and I say, okay, I have this crazy idea. I want a dual major in physics and nuclear engineering. And she goes, okay. And she just turns around and grabs the form and puts it on the thing. She's like, yeah, just fill this out and get it back to me whenever you can. And I was like, wait a second. I can do what I want here. No one's going to tell me that I can't do this or can't do that. And I was like, man, this is great. And so then I added the physics major. And then there was a general relativity course that I really wanted to take. And I had to take so many math
Mm.
prerequisites to take that course that I was like, if I just take another 4 math courses, I'm going to have a math major too. So I might as well just do the math major
Jeez.
too. And so then I added the
Oh
math
man.
major. And when I did that, Bill Bogley, the head of the undergraduate program at Oregon State, he didn't say, "Oh, you shouldn't do this. This is too much." He shook my hand. He goes, "Welcome to the club." He was excited. And so
Mm.
Oregon State was just such a positive experience for me that they really just let me explore the upper limits of what I could do. And the result was that I ended up
Mm.
with 3 degrees in math, physics, and nuclear engineering in 4 years at Oregon State. And so, and it was all kind of based on that North Star of can I acquire as much knowledge as possible to kind of maybe be able to contribute to this nuclear engineering or this nuclear fusion problem in the future. And to be honest, even as I was adding all those majors and doing more and more, it was really just because I was like passionate about these subjects that were so complicated and interesting. I still didn't really have an idea that I was going to be doing any research.
Mm.
And I got lucky again. There was a professor named Juan Restrepo at Oregon State. I was taking a vector calculus course in my second year. At the end of my first year, and he. I handed in my final exam and he just kind of stopped me. I think he like literally grabbed my arm as I was handing it. He was like, "Hey, I have a project for you. Just send me an email." And I
Mm.
was like, okay. I had no clue. I had no a concept of doing research. I was not looking for advisors as an undergraduate. I was just taking my courses. And I emailed him, and he put me on this interesting subsurface flow problem where I learned a bunch about partial differential equations during my first summer uh, at Oregon State. And then he sent me to a conference in Washington, D.C. in the following November. And at that conference, I met a student named Roberto Colon de Quinones, who was working who would be my PhD advisor's lab. Just completely
Wow.
randomly. Yeah. So I meet him and he says, "Wow, you're working on a lot of things and you're a dual major in nuclear engineering and physics. That's
And you're a
interesting."
junior? Yeah. It's-
Yeah, and and he's like, have you ever heard of REUs? Research experience for undergraduates. And I was like, I have no clue what you're talking about in any way, shape, or form. I don't know what that is. And he's like, okay, well, he's like, come to my table at during this time at the conference, and I'll tell you about them. And he laid out these things that were called RUs, and he's like, realistically, if you want to get into grad school, and I was like, grad school. I mean, I don't even know what you're talking about. But he's like, this is the type of thing you need to do with your summers. And so at the end of that conference, I went home, made a list of all these RUs that I wanted to apply to, including one at Stanford. And then the first summer after that, I actually went to go work at the University of Chicago because I wasn't admitted to the Stanford REU at first.
Mm.
Um, and so I did some astrophysics the next summer at the University of Chicago, continued all my coursework, and then the last summer, in between my junior and senior year at Oregon State, I did eventually go to Stanford and do some work on a coaxial plasma accelerator for that summer. And so then I got to meet my advisor, and it was just a great fit. And he was kind of a strong advocate for me coming to Stanford. And then by that time, I had decided and knew that I was going to go for a PhD. And because I was just enjoying the process of research, and it all started with Juan Restrepo, just seeing a student that was particularly
Mm.
talented in his class, I guess, or was at least doing well in his class, and saying, "Hey, I want to give you an opportunity." And it just started right there. It was just complete luck. I ended up being at the same conference as
Wow.
Roberto, and then I ended up at Stanford. So it's like really I've just been following this, and then I did my PhD research was not in nuclear physics or in physics or in nuclear fusion at all. I was I
Mhm.
was manipulating electromagnetic waves with plasma. I'm doing plasma physics, and I learned a lot
Mhm.
about plasma physics during my PhD, but it's only now as a postdoc that I'm really working on this fusion problem. And so, but I am there. I'm now doing I'm now doing that work that I was so excited to do as a high school student. So that's the long-winded answer to the story, to the question of how did I end up here. But the reason why it has to be so long-winded is because I really didn't know what I was doing or what my future was really at any step of the way. In particular, I just got lucky to run into some really amazing mentors who helped me see what the right path was for me at the right time, and they encouraged me because um, I didn't really know or understand that I had talent, and I knew I was like smart. I knew I was good at math, sort of thing, but I didn't know that my ability to translate mathematics into physics and vice versa, to sort of be able to in a nimble way understand what you're saying about physics through mathematics. That's an area that I have a natural aptitude. I didn't know that, but it took a man who had a master's in physics to see that in me in high school and say, like, look, I have to tell you, I think he said, like, you're one in 10,000 in this area. So it would really be a waste for you to not use that, to try to push that. Um, to that high level, and I took his word for it, because why wouldn't I? He had a master's degree in physics from a great university, and so I was like, well, if he believes in me, I guess I'm in the right place. And then the same thing with Juan Restrepo, and then also my advisor at Stanford. He always was he was always in our corner. I think that's one of his strengths as an advisor. This is Mark Capelli at Stanford. You know, I'll tell us a quick story. One time, when I applied to graduate schools, I was lucky enough to get admitted to a lot of graduate schools, and I applied to a lot of different plasma physics programs, fusion, different areas. I didn't end up going to Stanford, which I had worked with Mark before, but in one of my interviews, there was a professor at Princeton that I had a rough phone interview with, and I told Mark about it later. And then I met that professor at a conference, and he was like, he kind of came up to me and he's like, "Who are you again?" And I'm like, I'm Jesse. I was like, we actually had a phone interview, and he was like, really? He's like, we did, because he was like, I don't remember you, and I was like, yeah. I was like, it didn't go so well, you know. And then Mark just stepped in and he's like, I'm glad it didn't go well. He's like, because you didn't get him, I got him, and he's just kind of like that, He just really like is like, I'm so happy you're here, and I believe in you, and I think I'm lucky to have you as a graduate student, and that just made me swell with confidence and made me believe that I could achieve something, and eventually, it helped buoy me to finishing my PhD. So, but anyways, that's the whole story. I hate to take up too much of the time just telling that.
No, this is awesome. There's quite a few themes there that are worth just sitting with for a bit. There's the mentors that you mentioned, and people who go a little bit out of their way and sort of like beach the matrix a little bit for you, and all of a sudden a new space of possibility gets created that you sort of begin to imagine the what a fork in the road, where the fork in the road can take you. There's also the tough decisions of balancing very difficult to balance things. I'm guessing the decision to transfer out of UCSD and staying home, and making the emotional, like taking into account your relationship vis-a-vis whatever, other sort of intranslatable, incommensurate values there may be between the two lifestyles. And sticking with it, and committing to it, and, finding fortitude and knowing that you're in the earnest pursuit of something greater. And then, there's the green lights that, like you just hit, and you sort of, that you're grateful for. And then there's one thing that I wanted to ask, from the very beginning, but I was so enthralled by the story, that something like nuclear fusion is so big. As in it's big in all kinds of magnitude. It's like the thing that makes, stars,
shine that therefore, like gives life to the entire planet. And there's the power aspect, there's the beauty aspect, there's the mathematical language of it aspects, there's the the limits of electromagnetism and heat and matter. And so I was wondering which one of those, as of I'm guessing 14-year-old or something, when you're at Berkeley and you're sort of like looking at the thing, nuclear fusion sounds, if I try to remember what I felt, when I was 14 about nuclear fusion, it was like the kind of thing the bad guy in the movie works on. But that's as far as, like I would push it, like I don't know what aspect called you first. And then as you started unpacking it, what other aspects started calling you. So how about we go there and say like, okay, what was the first ray of sun that, stepping out of
Yeah.
Plato's cave?
Yeah, I mean that and that's why I said it's the very, very first uh, feeling that I had. I don't know how to describe it. It's honestly, it's like a little woo woo. I literally think
Yeah.
that there was a list of words on a screen that I was reading on a web page, and one of them was just like vibrating. It was like it was
Yeah.
calling to me, and
Yeah.
I don't even remember looking at or clicking on any of the other links or any of the other items on the list. Literally, I mean, I might have recognized what they were or something, but like I read through them initially, and it was just like for some reason I that one was calling me. I clicked on it, I read about it, and I think the thing that just really grabbed me and captured me was just the the numbers. When you read about
Yeah.
nuclear fusion for the first time, you're like, what the hell? Like they'll be like, here's what we're trying to do. Okay, we're trying to create a star on planet Earth. That's essentially what we're doing, and the way we do that is we puff a little bit of plasma. And what plasma is, it's a material that we've heated to such a point that we've ripped the electrons off of it. It's a bunch of charged particles that
Yeah.
are moving around and affecting each other in all sorts of really complex ways. Okay, and then we heat this plasma up to 100 million degrees, and it's like Fahrenheit, Celsius, it doesn't matter at that point, okay? It doesn't matter whether
Who
it's
cares?
Fahrenheit,
Yeah,
Celsius,
multiply by 3. Yeah.
Kelvin, you're talking 100 million degrees, okay? I would read that and I was just like, what? That, is that a typo? How can that be real? And then I just continued to, I was like, so the really it's just the extreme nature of plasma physics that was like, how can we ever even hope to understand something like that? And then to me, things that are really interesting to me and things that really call me are things that are difficult. Like like I run every single day, and I actually really hate running. And I'm
Yeah.
signed up for a 50K race later this
Oh
year,
boy.
and I would never
Oh
imagine doing
Lord.
that. And I've run a few marathons at this point, and I literally just do them because it's hard. And so like I think that I have that little aspect of my personality that plasma physics to me is like
Yeah.
one of the scariest, most difficult subjects that like the top experts in in the history of plasma physics are all like, you know, insane
It's too
hardcore
much,
Russians
man. Yeah.
from Kurchatov Institute, okay? Like they're just the most impressive people, like the Lev Landaus of the world. So that to me, it's like I don't. It scares me. It literally makes me nervous to think
Yeah.
like, oh my god, how am I ever gonna understand things at the level of these genius level hardcore physicists. But it's also that's the part that's exciting is like
Yeah.
maybe I can figure it out. And so that's really what drew me into the problem, made me passionate about it, was like I was like just reading about how insane this was, and I was looking at the diagrams of these, like I remember the first time I saw a stellarator. And maybe when you edit the podcast, you could put like an image of a stellarator, like the Wendelstein WX7 and in Europe. It's like you look at that device and you're like, what the who thought of this? It is just looks totally outrageous. And so that to me is exciting. Something that I like seems like I could never. Yeah, I could try my whole life and I could never even come close to understanding it, but I think that it would be fun to try. So that's really what draws me to the subject.
There's another aspect that I think is worth highlighting too, that, there, nobody should even try to be shy about the potential economic impact of any kind of breakthrough in fusion.
Mm-hmm.
So there's like one thing that stood out to me was you saying, like I'm thinking of my economic prospects, and if I go to the family company, there's an expected value there that is probably greater than the expected value I have in this more unexplored territory. But then again, I think that like in the context of the research that you're doing, you're like, well, of all the possible, things to research, this is Moby Dick. This is like the big one. Um, and, and not just in terms of like there's the economic aspect, which is, cool and wonderful, but there's also just the empowerment aspect of it. That is, like the kinds of futures we can dream of if this technology becomes, even more marginal, beginning its slow snowball into commodification, then, we're talking about the next chapter in human capacity, right? And so there's that aspect of it, cool, that is very cool to me too. That is like you can find solace in those things, and I'm now sort of sensing the pattern of okay. The question that I was going to ask is, you have this dream about working on this project, but there's so many steps along the way that you just have to get through to be able to sit down at your desk and sort of like now say, okay, now I'm doing what I want. But I think there's something to that endurance aspect that I think is in my mind, or the way I think about the world, seems to be independent of the natural aptitude toward a given field. But when put together, make for a formidable combination. How was the experience of developing that endurance mindset and doing things just because they're hard? And, where does that come from? How do you nurture that? How do you keep that flame running hot in a world that seems to, the entropy of it and the gravity of it makes it really hard to do that?
Yeah, this is a great question, and I've never actually been asked particularly how did you develop that? Most people, when I talk to them about like the fact that I will, uh, like when I was at Oregon State, the maximum number of credits that you can take is 19 credits, okay, and 16 credits is considered like full time. It's kind of a typical quarter system, and there was one quarter in particular where I was taking 29 credits, and I was basically working
Oh my.
90 hours a week to accomplish that. And I remember talking to somebody during one of my summers at Stanford, and he's like, "What do you do?" And I was like, "Well, I wake up, I go to 6 hours of lectures because it was a miracle that the courses I had no temporal overlaps. Everything was perfectly. I just went and I had
Wow.
6 hours of lectures that were all back to back, and then I went home. And when I went home, I worked on homework until I went to sleep, and then I did the whole thing over again in the next day. And they would be like, how did you? They would just kind of be like, wow, you're just kind of that's just how you are. And your question is sort of making me realize that um, I actually saw there was a conversation between this is so like podcast sphere manosphere to bring this up, but I saw this conversation between David Goggins and Andrew Huberman, okay, and he was talking about that, and I can't remember the exact structure in the brain, but there's this structure in the brain that essentially only grows when you do things that you don't want to do. And apparently, there's this growing literature that shows that this structure is sort of the seat of the will to live. or the
Mm.
will to do difficult things, willpower in the brain.
Mm.
And so the conversation between the two of them was like, David Goggins' entire brain is composed of that substructure. but but I think that the truth is really when I was a junior in high school, um, I had just started a relationship with my girlfriend, eventual wife, and
Mm.
she's super conscientious. Okay, she's like she always does things the right way, and she would never not turn in a homework assignment. It was just like, you do your homework
Mm.
and you get things done, and you get the good grade and you get out of there. Like that was her. She's just a very conscientious person. And up until that point in high school, I was pretty lazy, to be honest. Like I was getting detention because I was showing up late to class every morning, and I didn't turn in a single homework assignment in my math class because the teacher had the structure where he had bonus points on the exams, and I would
Mm.
score perfect points perfect scores on the exams. So those would weight the grade to where I would still get an A, even though I never turned in a homework assignment. And I did feel super embarrassed when he would come by and be like, "Where's the
Mm.
homework? Are you handing it to me?" And I would just like hand him a notebook with nothing in it, or not say anything. And I could just tell he
Oh.
was just like, "Oh God, I hate this kid." but I was still, getting a good grade in the class. And so I had this sort of very conceited mentality of like, well, if I get it, I don't have to do the work. And and my girlfriend, eventual wife, really inspired me to like, you know what, I'm gonna give it my best this next year, my junior year. It's supposed to be, at the time, it's like it had the the reputation of being the most difficult year of high school, and I was taking all honors and AP courses, like the most tough courses I could take. And so I was like, I'm really gonna try, and I'm gonna see if I can get straight A's this year. And so that first year I worked hard, and I two things happened at once. I think one, I actually fell in love with learning. So up until that point, I didn't really ever pursue knowledge for just for
Mm.
knowledge's sake, for the joy of pursuing knowledge. And then I also think that a little bit about that brain structure that I alluded to. It was the first time that I really pushed myself. I was waking up early, I was going to school an hour before school to do these things that were called like quiz corrections, where if you got the wrong answer on a quiz in a history course, you could go in early,
Mm.
and and this is just the way the rules worked. You had to do it before school started, and you had to, write what the actual correct answer is and then why it's the correct answer. And you could get back half your points by doing
Mm.
that. So like, this was an AP US history. So the way to, if you wanted an A in that course, you had to do quiz corrections.
Mm.
And so, and I am not a morning person. So like for me, that was just like pulling teeth. It was just awful. And so that like those two things happened at once. I was doing something that required willpower, and then I was falling in love with learning at the same time, which then sort of like made me do more things that I didn't want to do, that made me work harder. And so I think that it just started a snowball where that substructure of my brain,
Mm.
that muscle of being able to do difficult things, just started to grow and get stronger and stronger and stronger, to where
Mm.
by in my senior year of high school, I think I took 6 AP classes, which was, I even took one AP class that was like, I stayed after school to take a AP physics class with that great physics teacher that I mentioned
Mm.
before. And so I was doing something. I was working really hard. And then when I got to university, I was ready to hit the ground running, and that's when I added the physical aspect, where I started to run every day, and that was at university.
Mm.
And so I think that it was very gradual, and it just started with making that initial step of challenging myself. Okay, this is supposed to be the hardest. I'm inspired by this person in my life that
Mm.
eventually became my wife, in no small part because I admire her, and
Mm.
how conscientious she is. Uh, I'm going to give this my best shot, and I think that it just worked the right structure of my brain, that eventually turned me into this maniac who will sign up for a 50 kilometer race, even though I absolutely loathe running. I can't stand it, but I do it every day.
Oh
So,
man. Yeah.
and it's just like a snowball, right? So like I get up in the morning and I do something I hate to do the first thing in the morning every single day. And I think
Mm,
that I'm just working that muscle, or trying to grow that substructure in my brain that gives me the will to try to do these difficult
mm,
things. And I've just continued to lean into it because it's continued to work for me. I've just been lucky that I've been rolling downhill since high school. Really, I haven't made any,
mm,
like you said, all those forks in the road. It turns out that I've always taken the right fork, and I think that a lot of that just
mm,
has to do with with luck and with being fortunate to have some great mentors.
mhm. Yeah, and well, there's another note there that I want to hit on because even in the thesis defense, I noticed that your wife played a significant, like, core part of your personality, but you're also in a position where you're devoting a lot of your time to these pursuits, whether it be the 90 hours of work at the lab or running a marathon, which is I mean, like, I run one and it took a lot more time than I would have hoped it did. How do you balance that? So how do you balance, being in locked in co-orbit with somebody and you're defining each other in terms of each other and very grateful and, like, edifying and beautiful, yet you're in a position where you also have to have independence and sort of like, share time in the right way. How do you think through that problem, issue, theme?
Hmm. Yeah, I mean it's extremely difficult, and it's something that I am still trying to work on. I mean, we just had a baby in October, and the reason why we're
Congrats. Wow.
thank you. So, but the reason why we started this recording so late in the evening is because it's like I got to put the baby to sleep. That's my job. So I give him his last bottle of the night, and I put him and I rock him to sleep. And luckily tonight he was super easy. But anyways, the you it's a huge challenge, and I didn't do it correctly for a long time. My wife at one point during undergrad, when I was and this was when I was in the total thick of it, the 90-hour a week, and where I'm like, normally during undergrad, the way I tried to do it is I tried to sleep very little during the week, but just get it all done by Friday night. And then I really wanted to try and have like a free Saturday and a mostly free Sunday. And like I would say about 75% of the time I was able to accomplish that. And that's when I could spend time with my family and then with my eventual wife. But there was some periods of time where I failed at that. And so I mean, she didn't see me for 3 weeks, 4 weeks, and she was like, at one point, she just said like, "Hey, this is not gonna work, and you need to figure it out." Because I'm not even seeing you. I'm not seeing your family. You're not seeing my family. This is just not gonna work. And then I had to make a change and make my relationships more, not just with her but with my family and with her family and the people surrounding me, my friends as well. I had to sort of realize that those were also important, and make them a priority at times. Try to balance that. The truth is like I if you put that much demand on yourself, I don't think you're ever going to get it perfectly right. um, but it's just a matter of trying to minimize wasted time. So like I remember, um, one of the things that the whole three majors at a time thing taught me is that when you say you don't have time for something, most of the time you're just full of it. It's just not true. You waste so much time during the day, looking at your phone, doing this, doing that, or like just simply not tying your shoes fast enough, or like little things like that add up over throughout the day, where you can claw a whole hour back. And so you just have to make certain things non-negotiable. Like for me, my runs every day, unless I am injured, I will run. So like if I have to be somewhere at 6 a.m., I'm gonna run. I'm gonna get up at 3:30 and I'm gonna run. It doesn't matter. It's a non-negotiable. And so, um, you have to make time with your family and your loved ones also a non-negotiable. A
Mhm.
thing there's no excuses that can come up that will make you not do it. So,
Mhm.
and so that's I think that's it's just what you do, and it's like brushing your teeth sort of thing. So, I mean,
Mhm.
I'm afraid I don't have anything really profound to add to the sort of corpus of human knowledge on this this topic. I think really it's just a matter of like, you just have to make it a non-negotiable thing that you're going to do come hell or high water. And you have to put those
Mhm.
relationships at the same level of importance as the things that are most important to you in your work.
Mhm. No, and the reason I ask is because I saw the dichotomy of somebody of you being so dedicated with work, but also still even in the context of the showcase of your work, you're still giving the right amount of time and emotional energy to highlight the figures that got you there. Um, okay, but now let's talk about your um, PhD a little bit more because the thing that struck me about it is how many layers of abstraction you were able to tune into and find this through line that happens to be another massive society shattering possibility. That is optical computing and leveraging your knowledge of plasma and these very dynamic physics to deploy like I think what is to those in the know maybe like the frontier of computation. But for most people probably they don't know that the limits of Moore's law and like quantum
Mm-hmm.
tunneling and the limits of 2D chips that we can't stack in 3 dimensions because of heat.
Mm-hmm.
um, or even things like a rough estimation of how electrons move in a computer and that powers the speed of the things that we consume, but how different that is from the speed of light.
Mm-hmm.
And all of these other properties have become apparent once you sort of start digging into the different methods and different ways of doing optical computing. Um, and so I'm seeing a picture of you have this vision of nuclear fusion as I mean, I'm informally say something like the holy grail. And
Mm-hmm.
so in the side quest that you take, because you're sort of doing the things that you need to do to get to the point where you can devote your time to studying the holy grail problem, you're like, okay, well, but if I stack all of these things together, nice and well, I get this other thing that also kind of looks like the holy grail. And, it's very uncommon to see a PhD thesis have 200,000 views on YouTube. Um, and so I don't even know exactly where to start, but there's an exciting component there. Maybe I can try hashing your thesis back to you and see if
Mm-hmm.
I at least we're like on the similar footing.
Yeah.
Um, so the idea is light moves in electromagnetic waves, and you can change the properties of how those waves move if those waves are moving through plasma.
Mm-hmm.
And you can use the fact that you can configure plasma according to the material and the voltage and the current and all these parameters that you can put into the plasma such that the effect it has on the wave is different
Mm-hmm.
and customizable. And then if you arrange a set of these plasma tubes in the right way, you can get the diffusion of that light wave to behave in a way that does computation. What
Mm-hmm.
that should mean is like if like this is obviously a very high level example, but it's in one of these slides that I think it wasn't in your thesis, but in another video that you posted. Is you show a picture of a cat and you just blast a picture of a cat into this machine. And on the other side, you might get something like the word cat spelled out.
Mm-hmm.
This is obviously like, like the very crude example. Obviously, like the scale of it is, at the level of logic gates um, and, uh, and sort of like doing Fourier transform type of stuff.
Mm-hmm.
But is that roughly the idea?
Yeah, I mean that is the idea, and I like that you focused on computational tasks that are uh, like sort of something like image recognition, right? Because I think that the
Hmm.
this the way that optical computing, at least in the near term, and when I say near term, I mean maybe like the next 10 to 20 years, will be deployed commercially is by having these components that speed up a specific task, like a
Mhm.
matrix vector multiplication, or maybe
Mhm.
even something that is meant to do image recognition at extremely fast rate. So,
Mhm.
as a part of a larger whole in some sort of greater computational system. Um, but yeah, I mean, the idea is that there's, in particular with plasma, you know, Freeman Dyson. I have this quote from Freeman Dyson in my thesis actually, where he says that, you know, plasma is just this exquisitely complicated thing, and he thinks that, he sort of posits in the quote that, you think that it has the aspects that are necessary for life. I mean, you think that you could encode DNA in plasma. It's like so information rich.
Mhm.
And so the idea is that you take this really information rich substrate, and it interacts with electromagnetic waves and electromagnetic fields in this really complex way. And so, because it has these complex interactions, you can take advantage of that space, that huge space of possible interactions, and maybe pull out some patterns that are useful. Like you said, maybe being able to look at an image of a cat, and then as the light passes through this device composed of plasma and other, maybe solid state components, the device will be able to tell you on the other end, hey, you're looking at a cat. And that computation happened at the time, at the speed at which it took for light to travel through this device, which might be on the order of, centimeters or a meter large, which is essentially
Yeah.
instantaneous. And the way that you would do that with with a traditional computer is you would build a convolutional neural network that's performing a bunch of matrix vector multiplication with an input image that has to be flattened into a vector. And there's a ton of
Mhm.
or not flattened into a vector if you're using a convolutional neural network. But anyways, it's a bunch of operations, cascading through these transistors, which are nothing. I mean, this a computer chip is basically a bunch of transistors that are wired together with these extremely tiny aluminum wires, basically, and it's
Mhm.
just really really dense. But like, the actual architecture of computers is the exact same as it was when it was, vacuum tubes and they were in a huge building. It's really just a bunch of circuits with transistors, and the electrical signals are cascading through all those transistors. And so the physical signals are going through these transistor circuits in your computer and computing that result. And so, in a way, like, an optical computer is doing something that's both more simple and a lot more complicated at the same time, in the sense that you're taking something that's way more, physics and information dense, and then using that
Mhm.
to have this very simple process, which is just light passing through the device very quickly, but all of the processing is sort of like happening within this physical substrate.
Mhm.
In the case of my thesis in plasma, somehow. And like, to say that I like totally understand, that's the whole idea of bringing these inverse design techniques to bear, where you
Mhm.
just say, I want it to tell me that this is a cat, and you feed it a bunch of
Mhm.
examples, or you tune it iteratively to perform that task. I would never say, oh, you want it to turn into a cat. Okay, well, here's the exact set of plasma density within the tube that you would need to do that. I can just think of that. That's never going to happen. But that sort of was the novel contribution of my
Mhm.
thesis, was like, let's find a way to iteratively tune, and automatically tune the plasma density of all these elements to perform that complicated task. So, but yeah, I think you have a great general idea, and that's really the core idea that I wanted to get across was, imagine a future where we have these devices that do crazy things like image recognition, or something a little bit more conventional, but also incredibly important, like a matrix vector multiplication,
Mhm.
but doing this operation at the time, in the time it takes for light to pass through the device.
You know, Well, and I think it's also easy for people to overlook just how computationally extensive some of these functions have become just because of the volume that we do them. So like, I think the example of ChatGPT, it's a commodity type of user interface and a commodity type of product, but the hardware that's running in the background in some data center is pumping a lot of juice, and it's proportional to the input, it's proportional to the output. And something like your vision, it's it's not passive, but the computational expenditure is not proportional to the input. But I think I hadn't picked up on the fact that you're right. It's not Turing complete in the sense that it won't have loops. But most of these architectures are pass through, and you're sort of just applying a whole bunch of filters and functions and mappings and non-linearities and whatnot. And like at the outset, you get the evaluation that you want. So, and I was going to bring up inverse design because I think that was the moment where I was like, all right, okay, so this guy's working on another level, because also the insight that you had to contribute this to the field is a phenomenon of modernity. I don't think you could have come up with this idea 20 years ago. Of sort of saying, wait a minute, like let's do declarative programming on the hardware, and say, this is the structure that I want, and the thing will tune itself, right? Let's unpack that a little bit first. Like, what was the inspiration to draw on to say, I have this machine, this is what I think it can do. There's no way to program it unless it programs itself. Let's take that road and see where it takes it.
Yeah, absolutely. So when I came to my lab, we were building these things called plasma photonic crystals. Okay, and what a photonic crystal is it's just a periodic structure of some sort of dielectric material, meaning like a material that stretches or compresses light when the light it propagates through it. Okay, and if you come up with a periodic array of this dielectric material, and your crystal is large enough, what happens is the allowable propagation modes, bulk modes. So like if you're looking at the entire material as a bulk material, the type of modes that are supported in it collapse down to this discrete set of possible modes. And it can be very interesting where like it might be a type of material where the light has to be pointed in a one specific direction. And if you have let's say you have green light, so it's at a specific frequency, okay, or a specific wavelength, the light has to be pointed in only this direction. And if it tries to, if you irradiate the material at any sort of off angle, it'll just reflect off. It'll be like a perfect reflector. So imagine something like that, where like you could use that. So like let's say you're in a space battle. Okay. This is like an imaginary scenario. You have two spaceships, and you have one over here, one on the other, and they're trying to communicate with each other. And you have another ship that's somewhere else that's just blasting all of the frequency ranges with total massive loud Gaussian noise. So you can't communicate on any frequency band, and you're like, it's frustrating because you can't communicate with this two ships. Well, imagine you had a photonic crystal structure that only allowed light in from a specific direction. You pointed that detector directly at your ship that you wanted to hear from. And then that ship points a laser at the correct angle. And then you guys are like whispering to each other. And all this screaming that's happening from this person who's trying to jam your communication bands is just reflecting off because it's not pointed at that perfect direction, unless they were literally perfectly line of sight between your detector and that. So like that's the type of stuff that we were doing, and we were building these types of metamaterial, well, really photonic crystals, but I sort of put that under the umbrella of metamaterials, even though that's maybe not perfectly correct according to some folks. But I came up with my own definition of metamaterial for the thesis because it's just easier to talk about it that way. Go ahead.
But I think there's great validity to your claim that this is a metamaterial, maybe not in the isolated project of finding these photonic crystals, but in how you're approaching the problem of tunable via plasma photonic crystals, then you get the meta component where you can sort of do an over-the-air update, and it has a material, effects that can happen. But now you got me thinking about cool other stuff. Like instead of angle, if it could be frequency, and if it could be frequency, then the material could be a cryptographic key, and so then you're actually like legitimately whispering, and that is incredibly exciting stuff. So it's like, and honestly, just sitting with the concept of a photonic crystal sounds awesome. There's like a crystal of light and a structure that, like will make light behave in a certain way. When you went to the space battle, my initial gut example was sunglasses, or just a screen that filters out light and makes slightly different states. But
I'm a bit of a sci-fi nerd, I suppose. But yeah, it's funny because the reason why I thought about that is because I have a good friend who's still back in the Bay Area. But we were just having a text conversation about the logistics of a space battle and like how you would do communications and stuff. So that example just popped into my mind. But yeah. So the to continue to answer your question, these are the types of devices that were being built when I arrived at Stanford, and we were making them like arrays of cubic arrays of plasma rods, okay, which are just like discharge tubes. And we hadn't really tried to do anything super complicated with them. The first things I did was I tried to step them up in dimensionality. So we published a paper where we had like this wood pile configuration of plasma rods, where up until that point everything was two-dimensional. So like it was like the rods were all facing the same way, and then all of a sudden we had them like this three-dimensional structure. So that was a good paper and received well. And then I also tried magnetizing the plasma, because when you magnetize plasma, the way it interacts with light goes like completely crazy. You have this totally new zoo of possible propagation modes. If you're just talking about a bulk plasma now. And so now I say, okay, now we have a bunch of plasma elements that are all magnetized. How does that affect the modes that are now allowed in this photonic crystal structure? And then I started learning about this technique called inverse design, which is exactly what it sounds like. You come up with a device functionality that you want, like a priori, and then you encode your device domain somehow in a way that you can tune it, and then you just like choose a set of initial parameters, you tweak them all, you see how that affects your device objective functionality, and then you progressively iterate and improve your device. That's like a very simple way of explaining it, but that's essentially what we're all doing. And so,
but it's and I mean the sorry, I don't mean to interrupt, but I do want to say that the analog or the parallel between that and stochastic gradient descent, or whatever, we do for machine learning applications, and you're sort of searching the space, and you're fudging the variables, and you're seeing how the gradient gets computed, and you're chasing the gradient. I don't know. I think that there's a lot of familiarity with that concept that comes to me from the world of AI. And that's why I'm thinking of like, it's sort of like this novel-ish thing where like, it's the product of the last 20 years,
Yeah, exactly. And that's why we were interested in inverse design, because this is a technique that really it wasn't used en masse just because of the computational cost. Because when you do an inverse design algorithm, you typically have to run solve Maxwell's equations for a given domain for every iteration. And so we didn't have computers that could do this, where you could run 1,000 iterations within like a day or something on your desktop. That did not exist, even 15 years ago. And that's when these techniques were very, very first being implemented. So like, I imagine they were probably being run on university clusters, and it was probably taking like a week to do these types of things. And now for my thesis, we had really powerful workstations that we were using in our lab, but really all the computational work I did was like on a workstation that was just sitting at my feet. in my lab, and it would just like
mm,
I would run things that took like a few days to run sometimes.
mm,
But it's like the sort of scaling of computational power that we've had in the last, in the same goes for deep learning, right? I mean, the reason why we've been able to
mm,
deploy deep learning models, emphasis on deep, is because of this expansion of computational capacity that we've had in the last
mm,
decade or so. And so,
mm,
anyways, we were looking through the literature, and the way that inverse design was used up until the point that I tried to bring it to bear on a plasma device was essentially it was like a binarized material. So they would say like, okay, I'm going to have every pixel in the domain either have this epsilon, which is just the dielectric constant, epsilon equal 8, or epsilon equal 1, meaning vacuum, there's nothing there. And it's like we're going to tweak every pixel and see what kind of weird structure can come up, and we want to do a demultiplexer or a mode converter
mm,
or a directional beam steering device. Okay, and and they were very successful and came up with a lot of interesting devices. But in the end, these devices were static in single use. So like
mm,
they would etch the dielectric material via lithography or something, or laser etching, and they would make
mm, mm,
those devices that they had designed through the algorithm, and they worked really well. So it was like this really successful branch of research, and we had collaborated with a group at Stanford that was run by this professor named Shanghui Fan, who is just like he's the most cited, one of the most cited people I've ever seen. He has like literally hundreds of
wow.
thousands of citations. And so he's like one of the founders of the field of photonic crystals, and his lab had developed some software to perform inverse design. And so I was like, okay, I'm going to take that software and I'm going to, you know, insert the plasma permittivity and add some plasma elements to it on my own, and see if we can what sort of tasks can be performed with a
Mm,
device composed of plasma elements. And the reason why plasma is unique as compared to the binarized material or the static material domain is that if you use the plasma density of each of the elements as your parameters, you'll end up with one device that could potentially perform many functions, because you can reconfigure plasma in real time. You know, once
mm,
etch to the previous devices with lithography, that device was frozen and it was only
that's
ever
it.
going to do that one thing. And so, motivated by this idea of optical computing, where we might have to have these much more generalized devices. Like if you want to perform a matrix vector multiplication, like you don't want to just only be able to do encode one matrix in this device. You want to be able to do an
Mm,
arbitrary matrix. And so my idea was, if we inject plasma into these devices or make the devices completely out of plasma, we might be able to have these much more generalizable devices. In one configuration, it might do handwritten letter characterization or
mm,
identification. In another configuration, it might do a handwritten digit. So that was the idea, and we had some success, and we published a range of papers. But then it came time to actually try and build it.
mm.
And so that was a big
Yeah,
challenge.
let's talk about that and about going from, because there's one mode of operating that is consuming information and synthesizing it into insight. The whole different beast to then actually get your hands dirty and play with broken tools, and the power goes out and like, oh, the cable wasn't connected, and like all these more material problem. How was that leap of going from, okay, solid sound, let's see if it's valid in the real world?
Yeah, I mean, the luckily, a lot of my work in this area before I went computational for, really almost 2 years, like kind of around in that and during the pandemic. Um, and that's what the pandemic ended up happening at sort of the perfect time in my PhD, in the sense that I was doing mostly computational work during that time, so it didn't end up slowing down my PhD. But before the pandemic,
Mm,
I was working with the same types of plasma sources that I was going to be working on later on. So the whole time I was designing these devices in silico, and coming up with these device domains, I was thinking, I want to configure these so that in the future I will be able to build something like this. And I want the
Mm-hmm.
sizes in the domain to correspond to something that's experimentally feasible. And so I was always thinking about that. The big challenge really was finding out a mapping between because really the way that the assembly is this: you have a power supply. The power supply has
Mm-hmm.
some sort of current and voltage output that it's set to, and then you have this thing called a ballast circuit that converts that DC output from the power supply to an oscillating an AC signal that then goes to a discharge, and
Mm-hmm.
that's the plasma discharge that drives the plasma discharge. Okay, so that's the component of the system. So it's like what when I set it to 24 volts and 10 amps or whatever, what is the plasma density in the bulb? I needed to know that, and that was the big
Mm-hmm.
challenge. And then beyond that, how do I dynamically set that with a Python library for 100 bulbs at once, and then be able to iteratively improve the device in real time and just be able to like press enter and walk away. So that was like that was the big challenge. And it's the to say, I mean, really it was just it was testing a bunch of different things. I mean, I probably went through about 4 or 5 different methods for tuning the bulbs, that just were failed for one reason or another. It was like not feasible to remotely control them, or it would have been perfectly feasible to remotely control them, but the method that I was doing it was just like siphoning off too much power from the actual discharge, and it was just making the discharges go out at the lower plasma densities, or they weren't achieving a high enough plasma density, or would make the bulbs flicker and they weren't operating at some sort of steady state. And so really it was just a bunch of trial and error. And then, I mean, I will go to my grave with one of the best moments of my life being I had 100 power supplies wired up, and they were all individually wired to a single ballast, and then I had to make sure that the right power supply corresponded to the right bulb on the other end. And if you go and look at my thesis, there's this slide where there's a picture of the setup, and it's just like a mountain of wires. And I had to make sure everything was meticulously labeled so I didn't make a mistake. And I will always remember this. I had this like test script that used the library that I had written to set up the array and run it in like a specific configuration. And I was like, my heart was just pounding. I was like, I don't know if this will work. And it was like the very first time I had tried the whole array at once, and I pressed enter and it worked. I didn't even have to like troubleshoot. It was like a hallelujah moment. So like that's always going to be a huge victory moment for me. But yeah, I mean, really, it was just a bunch of like there were whole weeks where all I did basically for the whole week was like cut the wire here, strip that layer, pull these two wires apart, strip that one, secure into this like little connector, move on to the next one, and do that 100 times in a row. And then wire everything up. It was just like it was a lot of monotonous work, but the payoff was genuinely worth it, which is kind of crazy to say because it was a ton of monotony, but it really was worth it. It was like a great victory.
No, there's the reason I asked is because there's a in my mind a very stark difference between creative mode and robot mode. Where creative mode, you need to sort of open up the sensitivity, sort of like have a little bit of the of both sides of the brain on, and you're receptive to the feedback of the exploration that you're doing. Right, you're pursuing a thread, and you're not really sure what it is, and you're exploring this idea. You play with an equation. Oh, it looks pretty. Oh, but what if I did this other thing? And sort of like you're in this, I don't know, walk in the woods type of mode. And then there's robot mode that is like, this is the algorithm, shut up and get it done. Yeah. And as somebody who really enjoys being in creative mode, it's very hard to transit. Then again, you get into flow state. Like there's a
Hmm.
contemplative Zen aspect of it that is just like, I'm going to let myself go. I commit to the fact that this is what I'm going to be doing this week. It's not going to, it's going to be okay. I'm going to enjoy it. The thing that really messes me up is switching between the two and having to
Hmm.
switch, sort of like repetitively. I think that and I'm guessing this must have happened, especially like as you're earlier in the iterations where you make a scheme, you build it out and you want to get quick feedback and then you go back to the drawing board and then eventually they become, more stable and more, how do you balance in the sort of like this cornerstone period of your life where like you're about to ascend the mountain and you're about to get the title that you want that's going to let you pursue the things you want. How did you balance the frustration of flipping between the two?
Um, it's funny because the process that you describe of sort of being exploratory and then like that is just that's what a PhD is like, and in a lot of ways that's just what research is like when you're doing. I imagine that's probably what any type of creative work is like, where you wander in the woods, and then when you finally find something, that's when it's time to do the work. And I think that uh, the transition from wandering to going into monotony mode actually for me is a bit easier because I'm so excited when I find the right way to do it. Like when I tested the circuit and measured the plasma density and saw that I had this beautiful tuning curve from zero point 0.4 gigahertz up to 14 gigahertz for and this is the plasma frequency, which is just the same, essentially the same thing as the plasma density. They're intimately related. Higher plasma density means higher plasma frequency. But anyways, I had this beautiful tuning curve that I had come up with. And when I had that, I was like, let's go, let's build it. And it was like, I had all the motivation I needed to spend those couple of weeks cutting and stripping wires. Cause I was like, I figured out the hard part. Um, the hard the diff and it was like that in my whole thesis or throughout my entire PhD. Like it would be like the creative part is designing the experiment, like creating, like I did a lot of I built a lot of scaffolds for plasma bulbs in my PhD thesis because you have to arrange them in these strange arrays, right? And the creative work was like literally doing computer aided design of these scaffolds and then printing them and iterating and making sure everything fits all nicely. And I always like, I took a lot of pride in my experiments being rock solid. Like whenever I was mentoring a young student in the lab who was doing some experiments, I would tell them, I want you to imagine that the big one is going to hit and the building's going to fall down and you're going to come back and say my experiment is still standing because it's so solid. And so like I really enjoyed building like these really well designed and strong structurally sound experiments. And so that was like the a creative part. And then it was just like, okay, now I've designed the experiment, now I run the experiment. The hard part is once you've run the experiment and it's like, okay, now I have to transition back. I have all this data. I have this like physical material that I've mined, from the earth. And now I have to try and make something with it. And it's a transition back into like the creative mode so that you can communicate what you've learned, having used this tool that you built. And that transition is harder for me. So like because I don't think of myself as a overly creative person, and like as you can tell, like I'm definitely a grinder. So like for me, like if I just have to do something monotonous for a while, I just like accept it and I just do it. Whereas like if at the end of the cycle, it's okay. I did the push. Now I have to like synthesize it and I have to be creative and I have to find a way to communicate it. And then when that's done, I have to think of the next thing. And you sort of hope and pray that the next step will be obvious, but that's not always the case. Especially during like when you're still learning, when you're doing some of the first serious research of your career during a PhD. So Um, I think that for me the big challenge was going from the monotony to the creative. And like I said, I mean, I think that luckily most of the time the next steps in the communication was it was there. It wasn't obvious, but at least I knew, I felt like I knew what I had to do. And in the times where it was more challenging, I just kind of leaned on my lab mates and my advisor, who's a super, my advisor is super creative guy. He is just like, I'm just going to be mining him for research ideas for as long as he'll allow me to, throughout my career, because he is, that's one of his talents. He just can come up with ideas. And so, for people like me that may be challenged or are challenged or have difficulty with the creative side, I would just recommend to surround yourself with creative people. My best friend during grad school, my lab mate Ben Wang, who I said during my PhD, because I probably spent more time with him than my wife during my PhD. He is a total heterodox thinker. He is like, I just can't, like, he would just, some things come out of his mouth that I just cannot believe that he believes that, or like, or he has just perspectives on things that are just totally out of left field and nothing I would ever think of on my own. And a lot of my best friends throughout my life have kind of been that way. And I think it's because I gravitate towards people who can kind of fill out that non-creative side of me and help me think about things in new ways. And so, my takeaway from that experience is generally, try to find those people who can help you buttress the aspects of your personality where you might be a bit weak. And I think the same thing goes with like finding a romantic partner in life. My wife is I think really strong in areas where I'm weak, and vice versa. And I think that that's why our relationship has worked and remains strong to this day.
No, that's great. There's so many layers of abstraction packed into your work that it's fun to me to dissect them sort of diagonally and see sort of where the through lines are. Um, I also like one thing before we leave plasma. I think it's like remarkably beautiful how the sort of like metaphorical connections between rationality, lightning, light, and plasma, which is essentially what makes all of this happen in the first place. And I think there's something cool and self-referential about your work, especially in the optical computing part. That is how we're tuning lightning to be a better lightning, essentially, and help us make better decisions and inform rationality and guide the way, and sort of like in a more metaphorical way. But let's close out, because it's getting late and I don't want to keep you up, with coming home and the fact that you're going to be back in Oregon, and that it's coming full circle, and it feels like a beautiful thing that, the stars aligned in the sense that you're able to, you landed a faculty gig at
Uh-huh.
your alma mater, which is insane.
Yeah.
So let's go there. Like, what's that about, and how do you feel about it, and what do you got cooking for when you line up there?
Yeah, absolutely. So, I mean, it really is, it's another thing where, I mean, it's like you said, the stars just aligned. During my, at the start of my last year at Stanford, which I wasn't actually sure that was going to be my last year. I had a lot to accomplish, and I wasn't sure I was going to be able to do it and finish in like 5 years total. But I got this email from the mechanical engineering department at Oregon State. They had just recruited a new professor to sort of build an aerospace research program at Oregon State that didn't really exist before, because the students were demanding it. And so this professor's name is Richard Weirs, and he had come from University of California or UCLA, and he works on plasma material interactions and electric propulsion. And so it's honestly it's completely crazy. So I during the pandemic, I got a COVID puppy. You may have even seen her in the background here. So
I saw,
yeah,
yeah.
Yeah. We became friends with a bunch of other people who had dogs and got puppies at around COVID. She would play with all the other Stanford dogs at like 5 p.m. every day. Well, one of those friends of ours, she happened to have her partner was in grad school at UCLA, and she said, like, we were just talking about the things that we research or whatever. She's like, "Oh, you do plasma physics? That's interesting. I'll tell my partner about it." Because he does plasma physics at UCLA, and and so she tells her partner about me, and then her partner goes and mentions me to Dr. Weirs down the line after he's already decided to go to Oregon State, and he said, and he was trying to think of postdocs to come and work with him and help build out this aerospace research center, do some of that groundwork. And this person said, "Hey, well, what about this guy? I heard about him from my partner down at Stanford." And he looked at me and he's like, "I think this guy might be a good, forget a postdoc. I think he might be a good faculty candidate." And so he reached out with the head of mechanical engineering at Oregon State and said, "Hey, we want to encourage you to apply for this open position." And I was just like, "Well, I got to finish this year. this is, I just like, this is my shot." And because my wife and I always wanted to return home. And not only that, is I had this just amazingly positive experience at Oregon State. And there were some like kind of big shortfalls or things that I really wish I could have studied at Oregon State. Like the thing is when I got done at Oregon State, there was not a single professor that was doing any work there that would have made me stay. I was looking far afield, and so like I really hope that I can build a research program there that would have made me seriously consider staying. Even though I had gotten admission to a Stanford and an MIT. I mean, this is like a really big, like a dream. It's definitely a tall order, but I really want to bring aspects of things that like I want to have courses that really delve deep into plasma physics, and I want to do research in fusion and electrical propulsion and optical computing with plasma that would sort of really would have excited me when I graduated from Oregon State, because my experience there as an undergraduate was spectacular, and I think that it could be that way as a graduate student as well. So I went through the whole application process and convinced them that it was worth giving me an offer, and then I also I had an offer to do a postdoc here at Princeton to use machine learning to predict turbulent disruption events in fusion reactors. And so I convinced the folks at Oregon State to give me an extra year to come over here and do this work for a little bit, so that when I come back, in this coming fall, I'll have connections over here on the East Coast and be able to continue that work. And they were enthusiastic about that, and so that just became my plan. I'm here at Princeton at the Center for Statistics and Machine Learning here for 1 year, and then I'm headed to Oregon State, and then I think my research program, my lab that the name that I've come up with my lab, I'm not 100% sure I'm going to keep it, but I'm just calling it the Strongly Coupled Systems Lab, and the idea is that there's these systems that we call strongly coupled systems, and really what that means is just jargon for systems that have a ton of interacting forces and degrees of freedom that we do not understand, that are really hard to characterize. And like a plasma, like a fusion plasma, or like an optical computing device with a ton of elements, like these are things that we don't have an analytical description for. And so I want to take techniques like inverse design, machine learning, deep learning, and leverage those modern techniques to understand these systems that we don't have a good understanding of currently. And so that's really what my research program will be focused on, is using those tools in that way. And the three main areas are going to be in electric propulsion, and optical computing, like optical devices, and then in fusion, which I hope to continue doing the work that I'm doing here at Princeton. So that's the type of research program that I hope I'll be able to build out in the next, 5 years or so. And I've gotten involved in the recruiting process. I've been able to talk to some applicants, and that's super exciting. So I'm already getting stuck in, and I'm very excited. I'm very hopeful that we can do some fun work and build something to be proud of at Oregon State, and hopefully raise the profile of a university that's super great. And I think that unfortunately, a lot of for a lot of people, state university is kind of their only shot that they get. It's like it's really difficult to get into a place like Stanford or Princeton. And I'm like, I say this in the acknowledgement sections of my thesis. I mean, I still cannot believe that I am at these places. Like whenever I would walk through the main quad at Stanford and I would look at the memorial church, it's literally like coated in gold. It's like shimmering. And I'm like, what am I doing here? This is just amazing. And the same thing when I go onto campus here at Princeton and I walk by Nassau Hall, like where James Madison was educated. And I'm like, what? Like, it's just, I can't believe that I'm at this place. But, that's a rare privilege to be at a place like this. And I think that our state universities can be a place where a student can be exposed and get a taste of that same sort of excellence and rigor and excitement for all these exciting topics. And so I'm excited to go to Oregon State and hopefully be somebody like my mentors, like Juan Restrepo. I'm so excited to teach a class, see a student who maybe has no concept of doing research at all, but like tell them, hey, I just want to let you know that you are really good at this, and that is rare and valuable, and I want you to come work with me. And maybe it'll change their life, and maybe they'll go on to do really great things. So that's what really gets me excited about the opportunity to go back to Oregon State.
Yeah, it's amazing. I mean, I am excited to hear what you get up to. It sounds like you hit a lot of green lights, and I'm excited for you to keep hitting them. This was so great, Jesse. I really appreciate your time. Thank you for saying yes to this random interview, and I really appreciate and hope we can stay in touch.
Absolutely. Well, I thank you for the opportunity to share the types of things that I'm working on, and hopefully tell more people about the type of work I have planned. So I really appreciate it, and it's been an absolute pleasure.
You got it. See you soon.